All right, so in this linear programming problem, we are trying to figure out sort of the best mix of small and large filing cabinets. So we're told that the cabinet X costs $10 per unit and requires 6 square feet of floor space and holds 8 cubic feet of files, while cabinet Y costs $20 per unit, requires 8 square feet of floor space and holds 12 cubic feet of files. Okay, so we're given that we have $140 to spend and 72 square feet available for floor space. And we want to maximize our storage volume. Okay, so we first want to identify the constraints in this problem. So we'll say that we have cabinet X and cabinet Y, and we know that cabinet X costs $10 per unit and cabinet Y costs $20 per unit, and we know that that total has to be less than or equal to $140. That's the amount of money we have. We also know that cabinet X requires 6 square feet of floor space and cabinet Y requires 8. And we also know that we have 72 square feet available to us. So these are our two constraints. Okay. So then we're asked to figure out, well, what is the objective function that we're seeking either to minimize or maximize? And that is the storage volume. And we know that we're told that we have 8 cubic feet for cabinet X and 12 for cabinet Y. So what we're trying to maximize then is this function, 8x plus 12y is equal to our total storage area. So we'll call that S. Okay, so now we have everything we need to make our graphs. And that's what we will do, but we'll actually use Desmos. Okay, so let's start to enter our inequalities. So we have 10x plus 20y is less than or equal to 140. We have 6x plus 8y is less than or equal to 72. We're going to also add that x is greater than or equal to 0, y is greater than or equal to 0. Okay, so what that does for us is it creates this region right here where all of these overlap. And it's got 1, 2, 3, 4 vertices. And we know that we're going to get our maximum storage space at one of the vertices or along one of the sides of this four-sided figure. So we next want to incorporate our objective function, which is 8x plus 12y equals S. And we want to add a slider S to represent the storage space. And right now it goes up to 10, which clearly is not going to be enough. So we want to set this upper value to, I don't know, let's say if we had maybe like 120. Let's see how that does. Okay, so if we go up now to 120, that takes us up high enough. And what we can see is that we're going to get our maximum storage space at this point right here. And that point, oops, let's move this to 100. That point right here has coordinates 8, 3. And so what that means is that we're going to choose 8 of the small cabinets, 3 of the large cabinets, and that means that the total amount of storage space we're going to have is 8 times 8 is 64, plus 3 times 12 is 36. So 64 plus 36, which is equal to this 100 here. So that's going to give us our optimal amount of storage space given the constraints. Now, obviously, if these constraints were different, we might choose something different. By the way, if we were to find the slope of this line here, the objective function, we would have that the slope is equal to negative 8 over 12, or negative 2/3. And what that represents is the fact that for every time we reduce the number of large cabinets by one, we would be reduce and trade it for a small cabinet. We would be having a ratio of exchange of storage space of -2/3. In other words, the large cabinets hold, or the small cabinets hold 2/3 of what a large cabinet holds. Okay.